retina, cornea, fovea, optic nerve.
Well, the fovea is part of the retina,
Okay.
but it's good to you know that.
Iris,
Pupil.
sclera,
Sclera.
and
Did you say cornea?
mhm.
She did. Okay, cornea. All right. So we got the cornea, we got the iris, we got the pupil, we got the sclera, we got the retina. In the retina, we have the fovea. All right, and you just call the area surrounding the fovea the paraphobia or peripheral phobia. All right. Roughly, how many receptors do you have in your eye?
120 million.
Receptors total, not just rods.
126 million.
There you go. There you go. There you go. So you have 120 million rods, 6 million cones. What other types of cells do you have in your retina?
Rod and cone.
So those are your receptor cells. What other types of cells do you have in your retina?
Are you referring to like the bipolar cells?
Yes, bipolar cells. What else?
Horizontal cells, amacrine cells, and ganglion cells?
There you go. There you go. Good, good. All right. Good. All right. So, if we're talking about light, not light information, not visual information, but light, okay? Light passes through which cells first?
Ganglion?
Ganglion first. Bipolar. Ignore horizontal and amacrine. Receptors. That's right. That's right. Good. Now, what is the course of visual information or light information?
Goes backwards, you go from the sensor to the bipolar again.
Right, from the receptors to the bipolar to the ganglion. That's right. Good. What is convergence?
Can you repeat that?
What is convergence?
Good question.
How many receptor cells connect to a single bipolar cell?
Or ganglion. That's right. So how many receptor cells feed into a single ganglion cell? That's convergence. All right. How many receptor cells feed into a single ganglion cell? The receptor to bipolar cells, for our purposes, we'll just say is 1-to-1. All right. Now, rods and cones have different convergence rates. Let me get, so just kind of, there are around 1 million ganglion cells in your eye. Okay? But there are 126 million receptors in your eye. Okay? So, your rods have a convergence average rate of about 120-to-1. Your cones, 6-to-1 on average.
Is there positive ones last time? Did you say positive ones on the rods and cones 1-to-1?
No. So, on average, your rods have a convergence rate of 120-to-1. On average, your cones have a convergence rate of 6-to-1. But, towards the center of the fovea, it's 1-to-1. Are you all with me on that? But on average, cones have a convergence rate of 6-to-1. Now, that convergence rate has two downstream consequences. We talked about one of them. What was it? The convergence rate has two downstream consequences. We talked about the first one.
Cones can see more detail.
Cones can see more detail. Cones can see more detail. That's right. Alright. The other is that rods need less light. Rods can perceive lower intensity light. So how does that work? I'm going to redraw the diagram I had last time. We got our rods. We got our cones. Each of these has a bipolar cell. Now, each of these rods converge on a single ganglion. Each of these cones have their own ganglion. Alright, so again, we have our receptors, our bipolar cells, and our ganglion cells. Okay? Now, let's say that light is shown on every one of these receptors, okay? And let's say that a ganglion cell needs a net of 10 units of excitation to switch on, all right? And before we can perceive something, the ganglion cell has to switch on. Are you with me on that? If ganglion cells do not become active, we don't see anything. All right, because the ganglion cell is between the receptors and our brains. All right? So, let's say a low intensity light comes in and gives us an excitation unit of 1 to each of these receptors. That transfers down and we get plus 5 over here, but each of these only gets plus 1. Are you following me on that? Each of these excitations add up on this ganglion cell, so that ganglion cell gets 5. Because each of these has their own ganglion cell, each ganglion cell only gets 1. Does that make sense? So let's turn the intensity of the light up just a little bit. Now, each receptor is getting 2. Now this ganglion cell is getting what it needs to detect light. Each of these still not getting enough light. Does that make sense? We would have to crank up the intensity of that light all the way up to 10 in order for the cones to see it. Whereas the ganglions for the rods could see it with just 2. Does that make sense? Okay. So that is the second implication or second result of the differing convergence rates. Crap. I could have swore I brought my water. I did not.
For anybody who doesn't have it, that's number 45 on the study guide.
Yes. Okay. Has anybody ever seen the Mach-Band illusion? No. Okay. Well, let me show it to you. If this thing will hurry up. Excellent. What I'm about to show you is called the Herman grid. Just look at it. Just look at the center. Look at the center square. Now, out of your periphery, do you see gray spots here, 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 and here? They're not really there. Look at it directly. Those gray spots disappear. Those gray spots disappear. Right? All right. What's causing that is the same thing that causes the Mach-Band illusion. Mach-Band illusion. Alright. Do you notice how on the dark side, for each one of these bars, if you look at the whole picture, doesn't it look like it's going from darker to lighter? If you look at the whole thing, doesn't it look like it gets lighter on this side? Now, I'll try and do this. If you just isolate one bar, that illusion goes away. Because each one of these bars are a solid shade. Alright? Doesn't look like it. It looks like they fade. Alright? But that is the Mach-Band illusion. Okay? The same thing that caused you to see gray spots at the corners here is causing you to think that each one of those bars are changing in shade from dark to light. Does that make sense? So, what's causing it? What's causing it is a interesting little process that occurs in your eye called lateral inhibition. Now, lateral inhibition refers to the fact that each one of the the receptors in your eye inhibit the activity of its neighbors relative to the amount of stimulation.
Can you repeat that, please?
Yeah. The receptors in your eye, or the cells in your eye, inhibit their neighbors to the extent. Sorry, how do?
Stimulation?
Yes. Relative to the amount of stimulation. Alright. So I misspoke. It's not the receptors, it's the bipolar cells that are inhibiting one another. And they do that via horizontal cells. So here's what happens. So we've got our Herman grid here. Okay, we got a cell here, 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 here. Let's put an additional one on the end here. Okay? Now, there'll be some out here. So we're just going to focus on these 5 in the middle. Okay? Now, let's say that all the cells in the white spaces are receiving 10 units of intensity. Okay? All the ones that fall in here are receiving 0. Okay? Let's say that each cell inhibits its partners by 20% of its intensity. Are you with me on that? So, this cell is getting an intensity of 10, right? So how much is it, what number would represent the amount to which it's going to inhibit its neighbors? 2. So it inhibits its neighbors by 2% or 20% of the amount that it's inhibited. So 20% of 10 is 2. Right?
But is it not still receiving a 10 initially? Then
It is. It receives the 10, and then it inhibits its neighbors by 2 each. Okay? So this one here gets -2. This one here gets -2. These two are getting 0. 20% of 0? 0. So this one's getting -2 from this side and getting -2 from this side. But it's getting no negatives from the top or bottom. Are you with me so far? Let's assume this is going to do the same. So -0, it's going to get -2 from the other side, and -0 from the bottom. Are you with me? So, we take that 10 and we subtract all that's inhibited from it. Okay? So this one's going to end up being 6. This one's going to end up being 6. Okay. So, and this side's going to be the exact same as, this side will be the exact same as this one, right? For the exact same reason. Are you with me?
And the one in the middle will take -2 from both sides too, right?
And from top and bottom.
it'll be 2.
So that would make it
2, 4, 6, 8. Which means that center cell is acting like it's only getting an intensity of 2. Does that make sense? Whereas these act like they're getting an intensity of 6. Does that make sense? So that's why when you don't look directly at it, because when you look directly at it, you're putting more cones in that area. Does that make sense? And it kind of compensates for it. But if you were to look right here, this cone gets inhibited more than its neighbors. And so this area looks darker than these.
because it's not receiving as much light as.
No, it is. It is. But it's being inhibited more. That's what all these negatives on here mean. Alright? So this -2 came from this one. This one from this one. This one from this one, and this one from that one. Okay? So it's getting that 10. It's getting...
It's just getting it from just from...
No, it's getting the exact same stimulation that this one, this one, this one, this one, this one, this one, that every other neuron's getting, except these. These are getting 0.
Right.
But it's getting the exact same stimulation that every other neuron in the white is getting. The only difference is the amount that it's being inhibited. Alright? Is everybody with me on that?
And that's all lateral inhibition?
That's lateral inhibition. The neurons are inhibiting their neighbors. The more intense light they get, the more they're inhibiting their neighbors.
Is that 20%
What?
constant, or is it?
That was just for the example.
Okay.
Yeah, that was just for the example. Yeah. So, if we were to look at the Mach bands with this, okay? So we have our bars. Okay, so this one's white, this one's slightly
Can
shaded,
you pull it down a little bit?
this one's more shaded, this one's even more shaded, this one's even more, and this one's just black. Okay? Are you with me? So this one's good, so let's say you have a neuron here and here on each side. Okay. Now, remember, as it gets darker, they get less intense. Okay? So let's say everything in here is getting 100, everything in here is getting 80, everything in here is getting 60, 40, 20, 0. Alright? Are you with me so far? Okay. So, let's keep, just for the sake of this example, that 20% inhibition rate. Okay? So, this one, right here. Okay? It's getting 100 intensity, right? But so are the two neurons right next to it. So how much, so 20% of 100 is 20, right? So that means that this neuron that has the arrow above it is being inhibited from each neuron, from each side.
So a total of 40?
Right. So 100 minus 40 is 60. Okay? Now let's look at this one. Okay? It's receiving, the cell to its left is getting 100. So it's being inhibited from the left by 20. But the cell on its right is only getting 80. So how much is that cell going to inhibit it? What's 20% of 80? I don't know. 16? Okay, so 16 plus 20, that's 36. 100 minus 36 is 64? Okay, so we got cell 1 and 2. Alright, now let's look at this one. Okay? It's only getting 80, but it's going to get the exact same inhibition that the one before it got, right? Because on one side it's getting inhibited by 16, and on the other it's getting inhibited by 20, right? So 80 minus 36 is 80 minus 36. 44?
We got these calculators.
That's fine. Me too. Okay. Possibly, yeah. Now let's look at that one. Okay? So, it's getting 80 intensity, but it's being inhibited by 16 from each side, right? From this one and this one. So 32, 80 minus 32 is? 46. Minus 32? 48.
48.
So I'm just offsetting these so I can write this. This is, can't write them close enough. Okay, now let's look at this one. The same? Okay, now let's look at this one. So, it's getting 80, it's being inhibited by 16 on one side, but the one next to it's only getting 60. So what's 20% of 60? 12. So 16 plus 12 is 28. 80 minus 28. 80 minus 28.
52.
Don't be so annoying. Don't be so annoying.
I wasn't ready for that today.
Alright, so now let's look at this one. So it's getting 60. On the one on its left is getting 80, so it's going to be inhibiting it by 16. The one on its right is getting 60, so it's going to be inhibiting it by
12.
12. So 28, 60 minus 28, 32. And finally, let's look at that one right there. Okay, it's getting 60. It's being inhibited by 12 on each side, which means 24. 60 minus 24,
36.
36. Now, let's plot these, right? We have 60 going up to 64, down to 44, back up to 48. Stays there, goes up to 52, down to 32, and back up to 36, and it continues on. This one's actually up further.
And so this is the intensity of light.
Yeah. So this plot plots the intensity of light that you see.
And that essentially is lateral inhibition.
This is how the lateral inhibition creates the Mach band illusion. Right? Because remember, for each of those bands, you're getting, it looks really dark, and then it comes back up, spikes toward the end, and then gets really dark. Comes back up, spikes toward the edge in lightness, and then plummets back down in darkness. Comes back up, and it just keeps doing that. Does that make sense? Duncan, does that make sense? Okay. That is how lateral inhibition creates both the Hermann grid illusion and the Mach band illusion. Isn't that cool? I think that's awesome. It's like one of my favorite things of visual perception. Okay. Now, so that's how the receptors work. That's how some of the bipolar neurons work. Now, we get down to the ganglion cells. There are more than one type of ganglion cell. There are three. There are three types of ganglion cells. Primarily in the fovea, you have small-bodied ganglion cells called parvocellular. Ganglion cells. Alright, they're small bodies. They're primarily in the fovea. They project to the top four layers of the LGN. What does LGN stand for? Where does the retina project to?
Lateral geniculate nucleus?
That's exactly right. That's exactly right. So the parvoganglion cells are going to project to the top four layers, the LGN. Because they're coming from the fovea, what kind of information are they going to be conveying?
Color and detail.
Color and detail. That's right. Color and detail. Not only do they have small bodies, they have small receptive fields, and I'll talk about receptive fields here in a little bit. Small bodies, small cell bodies, and small receptive fields. And where are they located again? In or near the fovea, that's right. Now, as we move further out from the fovea, not only we transition from a majority of cones to a majority of rods, and we also move from parvocellular ganglion cells to magnocellular ganglion cells. These are larger bodies, and they have larger receptive fields. Okay. Okay, they're larger bodied and they have larger receptive fields. These project to the bottom two layers of the LGN. Okay? Since they are coming primarily from the peripheral retina, what kind of information and rods, what kind of information are they going to be primarily responsible for?
Shape and color?
Huh?
Shape and color?
Shape, not color though.
Shape and overall movement.
Shape and basic form.
Yeah.
Okay. They're going to be responsible for movement too, but
And what was parvocellular responsible for, did you say?
color and detail.
Okay.
Because they project from, you tell me, Duncan.
Top 4 layers of the LGN.
Not where do they project to, where do they project from?
Oh. You said fovea, I think?
Well, you can figure it out based on the information I just told you. If they carry color and detailed information, then you know they're coming from what area of the retina.
Detail is
And
Cone?
where are cones primarily?
We all just went brain dead.
Hang in there, you can tell me, come on. Where are there more cones than there are rods?
Oh, it's in our notes.
Somebody here tell me.
Retina. No.
Where in the retina?
Fovea. Fovea.
Fovea. The fovea.
I said that. That's what we said.
I know, but you asked me if it was right. You knew the answer. I was trying to get you to show yourself that you knew it. All right. So those are the 6 layers. We also have kiniocellular. Ganglion cells, and they project to a layer between or below each one of these. So underneath each layer of the parvocellular layer, there's a kiniocellular ganglion layer. Below each magnocellular layer of the LGN, there's a kiniocellular layer.
It's a layer cake.
Basically. Sure. You remember that image I showed y'all of the thalamus being bent like a knee? Alright. You could see each of the layers. Alright. I'm going to be honest with you, I haven't read what the kiniocellular ganglion cells carry.
Small cell bodies similar to parvocellular neurons, but they occur throughout the retina.
Both of which is true, but what they carry, I'm not sure. What information they carry, I don't know. So, just know that there are 3 types of ganglion cells. We know what these carry. I did some looking and I couldn't find it, but I'm going to continue to look and try and figure this out, but don't worry, it won't be on the test. If I don't know it, I'm not going to expect you to know it.
Just on 3 times?
Yeah, yeah. And that each of them project to a different layer in the thalamus. Now, really quick refresher question. What percentage of projections from the retina go to the thalamus? Huh? No, 90. 90% of the projections from the retina go to the thalamus. Specifically where?
Lateral genetically
the lattice-nucleate nucleus. Where did the other 10% go to?
Occipital cortex.
No. Where else? Where does that remaining 10% project to?
Superior collective.
The superior collective. Now, do what?
Control that.
There you go. Now, the 90% then that goes to the LGN then is routed from the LGN to where?
Occipital.
The occipital cortex. Specifically, the striate cortex. Or the primary visual cortex. Both of those are named the same place.
What was the second one?
Primary visual cortex.
No, one before that.
Striate cortex. They are both the same name. They are both the name of the same place in the occipital cortex. Okay? All right. Now, Hubel and Weiss did some work looking at the receptive field of neurons in the retinoganglion striate pathway. Okay? So they would look, and you know what I'm saying. The retinoganglion striate pathway. You know what that means. Right? Retinoganglion striate pathway. There you go. There you go. That pathway from the retina to the striate cortex that I just said, that is the retinoganglion striate pathway. Okay. Now, Hubel and Weiss look at the receptive fields of cells at each stage. So, they looked at the receptive fields of the cells in the ganglion. So they looked at the receptive fields of ganglion cells. They looked at the receptive fields of cells in the lattice-nucleate nucleus. And they looked at the receptive fields of cells in the striate cortex. Okay? Now, there are certain consistencies among all of them, but the cells in the ganglion, the receptive fields of the ganglion cells and the LGN are almost identical. Okay? And they have certain features. For example, the receptive fields are always circular. The receptive fields are always circular. The receptive fields of ganglion towards the fovea are smaller than the receptive fields of ganglion further away from the fovea.
Receptive field of ganglion.
Were smaller. So the receptive fields of ganglion towards the center have smaller receptive fields. What kind of ganglion cells can you guess those are?
Parvocellular?
That's right. As the ganglion cell goes away from the fovea, the receptive fields get bigger.
Magnocellular.
And we can guess that those ganglion cells are magnocellular. Good. Also, receptive fields for both ganglion cells and those in the lattice-nucleate nucleus have a center-surround organization. What does that mean? Well, it means that you have a center circular area that reacts differently to light than does a surrounding circular area. You have a center circular area that responds differently to light than does a surrounding circular area. Are you with me on that? Okay, now, for the ganglion cells, the bipolar cells that fall in here constitute its, first of all, let me back up. So you have two organizations. They're both center surround, but one's going to be on center and the other is going to be off center. Now what do I mean by that? What I mean by that is that when light hits the center of an on-center receptive field, that ganglion cell lights up. It becomes excited. But when light hits the surround of an on-center receptive field, that ganglion cell is inhibited. And then the exact opposite is true for an off-center receptive field. Does that make sense? So, let's focus on an on-center receptive field. So let's take this receptive field and turn it on its end like that. Okay? So we have our...
Lower.
We have our on-center and we have our off-surround. Okay? So let's imagine that there are receptors here, 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 and here. Okay? Each one of those is going to feed into a bipolar cell. And each one of those are going to fall into this ganglion cell. Are you with me so far? Okay. Light is going to strike just the center. Okay? It's hitting just the center. So remember, well, I'm not going to go into that. That's going to take too much time and it's going to confuse the hell out of you. So, these bipolar cells reflect where they are in the receptive field. Okay? So remember that this is an on-center. So what are these bipolar cells, and these three in the middle, going to do? They're going to send an excitatory signal. Alright? These are turned off by light, but since there's no light, what does that mean?
They're not going to inhibit her.
They're not going to inhibit, but they're going to be turned on. They're turned on in the darkness. Okay? So that means when light is only hitting the center, all of these are going to be sending an excitatory signal to that ganglion. Does that make sense? Now let's look at it again. All right, we got the same 6 bipolar cells, and they're all feeding in to the same ganglion. Okay? Now, light, somehow, let's say we create a donut flashlight. Okay? So light is only hitting out here.
Now, this is an off-center, right?
No, we're still talking about on-center. Okay? So, with on-center, basically, on bipolar cells are turned on by light. Off-center bipolar cells are turned off by light, which means they're on in the darkness. Okay? So, on bipolar cells are off in the light. Are you with me? So that means, and when they're off, they're sending inhibitory signals. Okay? So, what kind of signal are these three sending?
Inhibitory.
Okay? Now, these are normally on in the dark, but there's light on them now. So
They're all, yeah,
they're off.
so they'll be inhibitory too.
Exactly. So when the light falls only on the off surround, that ganglion cell is not firing.
It will not be activated.
No.
Because it's sending no excitatory information
Right.
to it.
Right. When the light is only falling on the center of an on center, it's really turning on. Does that make sense? Now, if light were to fall in here, but what would happen here? These would become positive,
But the three on the outside will cancel it out.
so we might see light, but not very likely. Now, if we were to cancel this one out, and this one out, so it's just barely crossing into it,
Make them. And then.
now we might see light.
To be able to see light. Yes.
Does that make sense?
And that's excitatory.
Now, this is all with an on center. With an off center, all of this is reversed. Does that make sense? Any questions about that? That's your receptive field. Now, that is basically how the whole thing works in, that is how it works in the ganglion. Basically, everything that we just talked about works the same way in the thalamus. The only difference being, it's not bipolar cells coming in, it's ganglion cells coming in. Does that make sense? Alright? But, the receptive fields change in the striate cortex. They're no longer circular. They're now bars. Okay? They're bars. So in the striate cortex, the receptive fields become bars. But they still have a center-surround organization. So if light feeds into the center bar, then we have activation. So mind you, okay, we have a cell in the striate cortex. It's going to receive a line, an axon, from a bar coming from the thalamus. Does that make sense? So it's not a line of cells in the cortex. Each cell in the cortex is going to get a line of input from the thalamus. Does that make sense? If we get input from the surrounding bars, it inhibits it. Are you with me on that? So, let's say that light falls right down the middle. Okay? Then this cell right here, it gets a lot of excitatory signals and no inhibitory signals. Does that make sense? But if that light is slightly off to the, slightly slanted, okay, so that it crosses, you're going to get an excitatory signal from here and here, but you're going to get an inhibitory signal from here and here. Does that make sense? Which could cancel out the activity in that neuron. Does that make sense? Okay. All right. That's how receptive fields work, right there. Now, you have different types of cells in the striate cortex. you have simple, complex, and in-stop. Simple, these are all called feature detectors. Simple cells in the striate cortex. Where's the striate cortex? In the occipital lobe. Simple cells in the striate cortex only respond to light at a specific position in the visual field and at a specific orientation in the visual field. Position in the visual field and a specific orientation. Does that make sense? Complex cells. They will respond to light at any position but only a particular orientation. So they'll respond to a 45 degree light anywhere in the visual field. Does that make sense? In-stop cells respond to light anywhere in the visual field except past a certain edge. Does that make sense? So, for example, if this is the entirety of your visual field, let's say that this square represents the entirety of your visual field. One in-stop cell will respond to light anywhere on this side of that edge. Does that make sense? If light falls on this side of that edge, it's not going to respond. Does that make sense? And you have an in-stop cell reflecting every possible potential edge there could be in your visual field. Does that make sense? So, how then do we see complex things like faces, patterns? All of these cells work together and create basically a very, very, very high definition pixelated version of your world. Does that make sense? The in-stop cells allow you to identify the edges of things. And you have an in-stop cell that allows you to identify an edge everywhere in your visual field. Alright, so even though I'm looking up at you and this table is now in my lower visual field, I have different in-stop cells not responding to anything beyond this point. When I look down at it, it's different in-stop cells. Does that make sense? So your brain can calculate, okay, which in-stop cells are responding and which aren't? Okay, alright, well that means that nothing passes, there's an edge at this point in my visual field. Does that make sense? Okay, alright. Crap, okay, we got some stuff to learn about color perception, okay? We see roughly between 400 nanometers and 700 nanometers of the electromagnetic spectrum. Okay?
Repeat that again? 400, 700 nanometers of the...
Electromagnetic spectrum. Light that is just shorter than 400 is called ultraviolet. Light that is just longer is called infrared. Why? Well, because short-wave light that is visible is violet or blue. Long-wave light is red, or at least we perceive it to be red. Are you with me on that so far? So, now, how do we perceive light? Well, there are two theories that help us to understand how we perceive light. The first is the Young-Helmholtz trichromatic theory. According to the trichromatic theory, our ability to perceive color depends on the relative activity of three kinds of receptors. Our ability to perceive color depends on the relative activity of three kinds of receptors. Those receptors are a shortwave receptor, cone, a medium wave, and a long wave. Okay? So, in order to see blue, you have to have a lot of activity or a large response in the short wave, but a small to no response in these two. Does that make sense? To see red, you have to have a large response in the long wave, as a medium to small response in the medium, and no response in the short. Are you with me? In order to see green, you have to have a large response in the medium, and a medium to small in the other two. Are you with me on this? Okay. Really just become very acquainted with the visible spectrum. You can ignore this one right here because it's your rods, and rods don't see color. All right, but here's your short wavelength cone. This reflects what it's receptive to. So your short wavelength cone is it has its biggest response to about, in fact I had the exact number, 400 some odd nanometers. 419 nanometers. So your short wavelength cone has its biggest response to light that is 419 nanometers. As you move away from 419 nanometers, its response grows lower. Does that make sense? Your medium wavelength has its maximum response. It responds the best to 531 nanometer light. As you move away from 531, either above or below, its response drops. Does that make sense? Your long wavelength responds best to 558 nanometers. And as you move away, its response drops. Are you with me on that? That is the trichromatic theory. That is Young and Helmholtz trichromatic theory. However, it doesn't explain things like afterimages. Okay? We have time for a quick example. Okay. Okay. Look away from the screen for a second. Okay, look at the screen. All right, I want you to stare at the crosshair. Just stare at it until I tell you to stop. Keep staring. Close your eyes. Do you see the American flag in red, white, and blue? Close your eyes. Do you see an after image of the American flag in red, white, and blue?
I don't really see the color, I see the shape though.
How many people see the colors? Did you stare right at that crosshair the whole time? Well, trust me, unless something's wrong, normally you'll see the red, white, and blue. Why? Because the opposite of yellow is blue. The opposite of black is white, and the opposite of green is red. The opponent process theory suggests that we see by several opponent processes. All right? You have a red-green opponent process, a blue-yellow opponent process, and a white-black opponent process. There is no such thing as a reddish-green. There is no such thing as a bluish-yellow. All right? A bluish-yellow is green. All right. The reason these colors don't exist is because we can only see red or green. We can only see blue or yellow. When we see red, green in that part of the eye is inhibited.
So like the film, reverse negative film when you go across the film?
Yeah. So these colors in the negative would have these colors. Does that make sense? And vice versa. Alright? And there's a complex mechanism to it that we don't go into in this class. We'll go, if you ever take sensation and perception, we'll go into it there. But, what you need to know is that red inhibits the processing of green, and vice versa. Blue, actually, here's what happens, okay? With these processes, you can only perceive either or. You can only perceive red or green, okay? So what happens is if a particular ganglion cell has activation above a threshold, you see red. If it has activation below a threshold, you see green. Does that make sense? So every cell in your brain, they're not all dormant when they're not being used. They have what's called spontaneous firing rate. Okay? If you move above that spontaneous firing rate, you see red, or blue, or white. If you move below that spontaneous firing rate, you see green, or yellow, or black. Does that make sense? Duncan, does that make sense? Okay. Alright, the last thing we need to talk about is color constancy. Okay? Color constancy refers to your ability to see a color consistently regardless of the lighting. Your perception of color remains constant regardless of lighting. Okay? Now, it takes some time to adjust. Okay? So, for example, light bulbs. They project light at a different wavelength than the sun does. Okay? Specifically, lights favor high wavelength colors. Alright? So, the light that you're receiving inside, you're actually getting more long wavelength light inside than you are outside. Light, natural light, it favors all colors roughly equally. Does that make sense? All wavelengths roughly equally. But inside, this light favors long wavelengths. So, you're actually getting more red light in your eyes in here than you are out there. Alright? So why doesn't everything look slightly red? Well, if you come in straight from a bright day into a room, it does look slightly red. Have you ever noticed that? But if you wait long enough, all the colors go back to normal. That's color constancy. Okay? Why does that happen? Well, your receptors fatigue. They selectively fatigue. Okay? So, all your long wavelength neurons, receptors, when you're inside, they begin to fatigue and they stop reacting as much. Does that make sense? That's called basically color adaptation or chromatic adaptation. Yeah.
So is that why if you go to someone's house where the TV has like the wrong tint the entire way, after a while you don't even notice it, and you can go back and look at your own TV and like, okay.
Yeah. Yeah. Well, I mean, if you look right at it. Yeah. Because if there's too long between it, then your eyes will adjust. Yeah. Okay. Any questions? All right, you got 5 minutes. Well, I'll stick around longer if you need me to. But exam review. Questions on the exam review?
I'll let them go first before I bombard you.
Okay. Questions? Everybody got the exam review on Saturday, right? Nobody's answering.
Yes.
Okay.
Pulling up.
Okay. We got no questions here, Jonathan, so go ahead.
Okay, number 23, you asked what happens in each stage of neural development.
Yep.
I have something on everyone except differentiates. I just have forms, axons, and dendrites.
And that's right.
Is that it?
Well, I mean, there's more to it than that, but that's essentially it, yeah.
Okay. What is chemical adhesion molecules?
CAM. So these are the chemicals that help in guidance and adhesion. So immunoglobulins. Chemo can help with it too, but they're not a type of CAM.
So immunoglobulins is the only CAM that we need to, that
We'll need to
we'll
know.
need to know.
No, I mean, you need to know that chemo can help with it too.
Chemo what?
CHEMOKINS.
Okay. And that has to do with the chemoattractants and chemorepellents?
Yeah.
Thank you.
Thank you. Chemoattractants and chemorepellents also are guidance molecules that help during differentiation.
Okay, and that's also for number 25, and we just put it's in the differentiation level and migration stage of neural development, and it attracts and repels.
Yeah, I mean, yes.
Okay, 1 second.
I mean, I don't remember the exact question, but
It just says chemoattractants and chemorepellents.
no, I mean, I don't remember the exact question.
Oh.
What it said.
Oh. Okay.
So it should be,
See, number 33 says the effect of exercise on neural preservation in old age.
Right.
I found something relatively close on 139, but it didn't give us, I didn't think we went over anything on it.
Well, about 5 minutes. So, remember how it starts talking about rats in an enriched environment seem to have thicker cortices, but then it may not have anything to do with the environment, but more to do with the fact that those rodents in an enriched, quote-unquote, environment had more physical activity. And then it went into humans. Elderly people who are more physically active tend to have less neural degeneration than do non-physically active adults. And then I mentioned a study whereby people who were exercising showed small but significant, statistically significant increases in cortical thickness.
Okay, I got it. 38 talks about are new neurons produced after early development, and if so, where are they produced and where do they help? And I have they can regrow at the peripheral nervous system.
The axons can, but new neurons can't.
Yes. New neurons can't.
No.